Thank you for having me, and Yanni, thank you for kind introduction. So today I would like to talk about, the idea about constrained fuzzing without paying too much. And really, it's based on some of the reflections that I have had, regarding actually building domain-specific customizer fuzzers from scratch. And then I was trying to basically draw like reflections on the effort that it took. And I hope to share some of the vision or new directions that our community could think about together on like how we can strive to bootstrap custom fuzzers without paying too much. All right, so before I go into the main part of the talk, I would like to give a brief background on the academic or like a research journey. So as a graduate student, I actually started early on with a lot of people in this community on like looking into mining software repository research, in particular, code clones or recognizing and leveraging redundancies in like recurring code patterns or recurring fixes. So, my work was on like building and techniques for like automating, detecting, and managing these code clones over the evolution of a lifetime. And I think really the change of heart for me happened in 2014. That was the time that I was going off for tenure, but I also took the time to visit Microsoft Research. And at the time, I actually did the studies of an emerging role of a data scientist within software team. And that helped me to recognize like importance of a data-intensive software development and the kinds of systems and engineering that goes around to build with a large scale of a data. So since then, I kind of moved into the space of debugging and testing tools for big data analytics. And that helped me to recognize some importance of a hardware heterogeneity incorporation to come up with a like more acceleration and performance enhancement. So, for the past probably 10 years, I've been focusing mostly on how do we really do software engineering for these AI enabling technologies, such as data processing or hardware heterogeneity. And now you might be thinking, what is its relation to fuzzing? If we actually, regarding this, I actually started looking into more interactive and automated debugging and bringing techniques like a taint analysis or spectra-based photo localization into space. But if you look at like papers that are appearing like after 2010, you could probably see the names of fuzz testing in the domain. Like a fuzz testing with the hardware probes, like framework abstraction and like natural fuzzing. And then also within heterogeneity, which is probably threads that I started around like 2020, you could see that I started with initial work on refactoring, automated transformation, or translating ideas of a repair to this domain. But later work or current recent work is actually mostly working with the term fuzzing or testing in that domain. So you might be kind of wondering why. And then let me just give you more anecdotal or like historical context. So when I was first looking into this space of big fuzz, I actually previously worked on big test, which is a symbolic execution-based testing with the framework abstraction. And I actually visited like UC Berkeley around the time of 2018. Again, I figured that was the time that I was going off a full professor, and I wanted to visit like Kushik-san and talk about this, a little bit of work that I wanted to say. Like I worked on symbolic execution testing, and he introduced me to his two graduate students at the time, Rohan Padai and Caroline Lemieux. And they were talking about something called the AFL. And I, at the time, actually, without any kind of, shame, I asked, what is it? Right. And then they said fuzzing. And to be honest, I'm going to be honest with you. I heard about a lot of people doing fuzzing at the time, but I actually didn't really understand, or I would say honestly, I didn't really have a lot of appreciation at the time because it looked so random and so brute force and so
compute intensive in terms of just throwing darts at the thing. And I was like, you guys look really like doing something interesting and amazing, but then here's the thing. So fast forward around 2018, when I gave a talk, I was still working a lot on this like big text and symbolic execution. And when I recognized that symbolic execution is actually really elegant technique, but once you get to a certain level, you have these, almost like it hits your face that, oh my God, I need to model every library, every API that I see in terms of symbolic execution constraint. And me and my students realized that we have done a lot of work. We published a paper, but then after this, we actually have to do a lot of engineering one at a time. And all this work is not done by like SPF. Now it's like your job to add everything on top of it. So I called Rowan in 2019 to ask at the time, like about a year after, what is it, this thing that you built called JQF, or is there anything I could do with it? So that was a discussion. And so today, as I said, I'm kind of jumping a little bit. So today's talk is like sharing some of these lessons learned from like big data analytics and heterogeneity in terms of building these domain-specific fuzzers. And from this second part of the work, I would like to share some like ongoing work, but more of a like future idea directions that we as a community could think about it together, which is how we should try to build these low-cost custom fuzzers automatically or semi-automatically by relying on pluggable and learnable components. Within this direction, I'm going to share one idea of a custom mutation synthesis from example. Then later, I'm going to share some ideas on like how we should maybe address this problem of automated grammar inference again, or like constraint synthesis from various sources, or lightweight DSL for context-guided input generation, where some of the authors in the room have been doing fantastic work in this domain, which is really exciting. So let's now kind of go back to the past and try to think about the lessons we have learned from the big data analytics or hardware heterogeneity in terms of writing the fuzzing. So I think I jumped around, but I already gave a context here. Like this was my first intro into actually building fuzzing for big data analytics. Okay, so what I mean by big data analytics is like applications that ingest like, terabytes or like, terabytes or like, like megabytes or gigabytes of data. And these are data processing applications. And when you think about it at a high level, it consists of what we call as a data flow operator or like relational operator, such as a filter, map, join, group by. These are represented as a green. And then the rest is what they call as a user-defined function. This is a terminology the database or data analytics community uses a lot, which is an application logic that developer writes, which is a custom code. So if you see this one, the green is these are like operator, which is often implemented in terms of million lines of code, because even though semantics is very concise, it actually is represented as a distributed application, scheduling, partitioning, like concurrency control, communication. There's a lot of things going on underneath. And then this application logic is the orange. So it usually compiles to bytecode, and the framework is really large. And I would say data flow implementation contribute to the most of the bytecode. So let's now think about like what makes it really hard to make it work for like fuzzing. So fuzzing is often built on the assumption that you could actually call target program in like milliseconds or 1,000 invocations in a second, mostly coming from like command line processing utilities or security domain. So in this domain of a big data analytics, context setup itself is about 10 to 14 seconds minimum. So that means every invocation has a minimum about 15 seconds setup time to do invocation. So the invocation latency is a real problem. Then another problem is, as we know, like bit level or byte level, these are low-level elementary mutations are unlikely to produce a meaningful input. the likelihood of doing that in a big data is much harder because the data itself has a very large footprint. So if you do random, selection and mutation, likelihood of coming up with a reasonable data is harder. Then another problem is that what people care about is actually really the branch coverage of application logic once you build a trusted framework works. But if you do conventional coverage guidance, then it will go into many different scheduling, error processing, fault tolerance kind of code, and finds all kinds of things as a coverage report, which application developers may not care. So now let's talk about then what kinds of a customization that we have done. First, the customization was actually what people call like proxy guided fuzzing sometimes. What we did is that we did a source-to-source manual rewriting automatically, not manual, automated transformation to replace the framework code with what we call as an executable specification. So if you look at the original Spark code, we will lift the bytecode generated from user-defined function. We will combine with the executable specifications in Java, which is almost like rewritten version of a simple map, filter, group by operator, which is much more concise but executable. We'll combine them together and then use that as a basis for fuzzing. The second idea is actually coming up with a new custom notion of a coverage that makes sense in that domain. As I said, we may not care about all kinds of coverage feedback that's coming from underlying framework. So what we did is that we came up with a new notion of what we call as a JDU. JDU stands for Joint Data Flow and UDF for coverage, so that we could listen to coverage feedback in the application code as is, which is coming from user-defined function. But we will combine into logical abstraction or logical partitioning of a joint data flow or joint operator or like a relational operator and combine together. So as a simple example, if you have an operator like a filter, you have two equivalent classes. One is a filter pass and filter doesn't pass. Or if you are thinking about join, you have join where left key matches right key, which is where join flows, or left key does not match the keys in the right table, and right key doesn't match left table, so that it doesn't proceed. So we model those kinds of possibilities. Then the third part is actually a lot of somewhat like manual insight, but translate into automation. So we know as a community now that coming up with the good mutator actually makes it work very well in a specialized domain. So me and my students look into some of these common error types in big data analytics domain using like Stack Overflow, and then lift it into kind of common transformation that's likely to trigger many different like known types of errors. So like these are like some of the things about data distribution mutation, data type mutation, or format mutations, or like column mutation. And these are really built by the insight that, big data analytics often does like semi-structured data processing. And there are certain kinds of errors that are more likely to happen. So this is a little bit expected result. Like it sounds amazing, but this is like almost a 1400x speed up really comes from replacing that target subject program that has a long latency to something much simpler and quickly executable. Then also code coverage, these are like improvement comes from these better way of dealing with the feedback. And this one, where we detected more errors than symbolic execution technique, really comes from the power of a fuzzing over symbolic execution technique, where symbolic execution gets up to kind of getting very good path coverage until the point you model. But any uninterpreted function that you didn't model, you don't know what's in there. That's where this big fuzz was catching up the remaining margin, right? All right. So now the second piece.
So around 2020 or 2019, I was kind of moving on to space of hardware heterogeneity. I think right now we are in 2025. My dad is a dentist, but he asked me about NVIDIA. So I think hardware is a big thing in current era where everybody is excited about. But at the time, I was actually more interested about this idea of acceleration or customized accelerator. Just because of the energy efficiency or kind of the legs that you could get by doing some of these big data analytics or kernel rewriting. So at the time, I was looking at this domain of like, how can we incorporate hardware or custom accelerators more easily in the development workflow? And looking into the space of CPU to FPGA, like kind of a migration, right? Like if you have a custom logic that could be migrated to FPGA, how can we help developers in terms of finding bug or help the migration process? And this particular work on heterogeneous actually comes after refactoring, where we realize that people want to do, if they want to do repair, what they want is like, in some sense, a good oracle that drives a repair. And we don't really have a good oracle other than just checking behavior on CPU versus FPGA. And let me tell you why these kinds of, what is the developer workflow and why these errors happen. So first, you have a host code, which it could be just a C application. What people do is then they profile this for a long time, and they recognize a particular logic that takes a very long time. Then what they do, in this case, is like, let's say KNN with a like accumulate operator that's taking a long time. Then what FPGA synthesis does is that map that directly into hardware circuit on a programmable circuit called the FPGA. And it's almost like building your custom like hardware instruction or circuit. So that part is taken into this kernel code, which finally compiles into RTL. But this kernel code is very finite resource constraint code. You need a bit width, not necessarily integer 32-bit integer that we're comfortable with, but it could be 9-bit or it could be 7-bit integer. Or there are like, like for example, every also logic has what they call as a pragma, which guides like how it should be compiled into a hardware circuit through root rolling or some of the optimization. So how do people do this now? It was very interesting to me that I learned that, one of my colleagues, Jason Kong in our department, they were graduate student building this accelerator. It's almost like a manual transformation and a lot of optimization thinking to come up with a new kernel. And coming up with optimized kernel is a like 3 to 6 months process with a very iterative work. And that is actually production of some of these papers that you see in FPGA or like design automation conferences like that. So, but if you want to do fuzzing to identify divergence errors, how long it would take? These are numbers that my postdoc back then, Qian Zhang, actually found. These numbers are incredible. It would take almost 90 hours to find a single bug. And do you know why? Can we guess why?
To debug.
Debugging is one thing, but there's actually even like obvious but like bigger problem. Hardware simulators are extremely slow. They are running in the order of usually hours. For a simple program, it takes about 15 minutes. So now fuzzing, which I thought was a challenge when it's working with the 10-second startup, is now translated into 14, 15-minute minimum, right? And that's what's really stretching it. So now let's think about then why you cannot use these fuzzing and hardware simulation domain. One, hardware simulation, for example, branch coverage makes no sense. Like, so actually Kushik and some other people, as well as other people, did this notion of translating coverage into hardware circuit. But if you actually talk to any hardware engineers, they create a parallel circuit with the multiple, like a
almost like a mux, like doing the computation simultaneously and they pick the right one. So this branch coverage at a hardware level, very low level, but also doesn't make sense because of the built-in way that hardware parallel circuits are built. Another problem is this effective mutation problem. Like, so if you are trying to find these errors between the FPGA and CPU, you must stretch hardware behavior in a way that stretches its finite resource limit. But hitting that by chance is actually extremely difficult if you do these random mutations. Then, as I said, the biggest problem is actually this one. And I hope that's what I think our community could think about. Once you change the picture of a fuzzing that works in a millisecond feedback to like 2-hour feedback, you really have to rethink of what fuzzing really means. So the problem is that this execution delay was a real problem. So we really decided to think about this from a perspective of designing like custom feedback that really makes sense in that domain. And we call that as a accelerator spectra monitoring. For those of you who were alive, some of my students actually born after this. So in Y2K, there was Tom Ball and, and other people at the time, worked on this idea of first coined the term spectra, but spectra is a kind of aggregation or a summary of a program behavior. And what we are trying to do is spectra that makes sense or a summary of a dynamic behavior that makes sense for this hardware accelerator domain. So what we did is basically designing these custom monitors using static analysis so that we could listen to this custom feedback that makes sense in domain. And how we do it is that we do static analysis that analyzes these inserted high-level synthesis pragma, which is almost a compilation directive or a macro that guides what the compilation of a hardware circuit should be, and then creating a custom monitor that is making sense for that transformed hardware kernel. So for example, that hardware pragma or type definition will say integer is an 8-bit integer, and also it's going to do data flow optimization and unroll factors over there. In terms of unrolling factor of 2, we create a monitor that actually checks for value ranges or access the offset or listen to the loop iteration and use that as a feedback. The other thing that we actually have done is this idea of a probabilistic mutation. I think, probably other people in this community also have tried multiple or similar ideas along this line, which is if you have several mutators, then you are choosing the activation probability or adjusting activation probability of a mutation based on the feedback we have gotten. So we will increase or decrease these probabilistic probability based on these monitored feedback that we're listening to. Then this one is similar to that, a proxy guided fuzzing. What we are doing is that we are trying to do early termination of a target simulator and compiler, because the compiler and simulator is taking about 15 minutes. So what we wanted to avoid execution as much as possible. So what we built is we built our own linting technology on Clang and LLVM, so that if so that was actually for the repair. But in this case, what we did is we will invoke simulator only if the behavior seems to be different from what we actually have seen before. So we will listen to what are the memorized ranges or size of a scene kernel input values. And when the values are different enough from previous one, then we will do invocation, but not the other. All right, so again, if you spend this much time customizing, then you get anticipated speed up as well as a bug finding capability. So as you could see, these are building blocks led to finding more bugs and speed up in terms of fuzzing. So this is a time that let's now reflect. And I hope you can take the time to reflect if you have built any custom fuzzers or did domain-specific of specialization, how much time you actually spent doing this, right? So I am now like showing like kind of this one is it could be controversial, so maybe you could and then my students actually told me to kind of look at the customization and check in a little bit in a more careful way. But let's first look at the type of customization that has happened. I categorize into mutation, feedback, and abstraction. The third abstraction, I'm mainly talking about abstraction for speed, where I reduce the invocation time or replace it as a target program so that it could execute fast. So if you categorize these papers, many of these insights are actually very domain-specific insights. After this big fuzz, we realized that what really matters is coming up with the natural data or dependency-preserving data. So we need a better mutations along those lines to make the data realistic. Or like some of these heterogeneous, once we built the accelerator monitor, then we realized that if we could leverage hardware level feedback directly in a very smart manner in terms of communications or in-kernel values, we could do better mutation. Then we also realized that hardware accelerator is not only target of a fuzz testing, it's actually enabling building block for accelerating testing itself. So we could, parallelize these lots of concurrent mutations using hardware feedback, hardware acceleration. So if you look at, and then I think we did also some work on quantum computing in terms of equivalent circuit generation, but these ideas are very similar to fuzzing in the sense that we were avoiding circuits that are not worth executing on IBM, at the time hardware, because it would be beyond the decoherence limit based on circuit depth. Therefore, we will avoid it, right? So these are how we categorize these customization. Now let's look at customization effort required for each fuzzer. And when you are working on this academic project, it's very hard to, calculate what is effort. So again, these numbers may not mean very much, but I do remember as a PI, I think each fuzzer took about 3 months minimum, more like 6 months. If you think about the time of understanding the domain to figure out what to build, and including time for presentation and other things, I think initial work took about 10 to 12 or 15 months. And then maybe some subsequent work had a little bit boosting by building on prior work, but I could tell you that it took significant amount of time. And let's not talk about just my group. There are, if you talk to people in industry, some of the fuzzers that are really loved by, are domain-specific fuzzers, like the ones that works really well for SMT logic, or the ones that work well for database engines, or, our beloved C-Smith that has been around for a long time, or MLIR Smith, which are for multi-layer extension compilers. If you look at the effort, it's actually significant development. And if you look at these successful fuzzers, in the domain of SMT and databases, once the idea bootstraps, a lot of effort is built on plugin to make it work for different dialects of SQL, right? To support more different kinds of logics of SMT. So there's a lot of customization that makes these custom fuzzers thrive and successful. And if you now have to think about what is the most important slide of today, I would say this slide. I've been thinking that what I've been really doing is actually making customizations in 3 angles. One is mutation and generation. The other one is a feedback. And the other one is reducing that execution. And why do I put yellow, but in a different shade? As you can see, input mutation and generate has a darker shades than execute, which is a light shade. Let me tell you why. The reason why is that I realized that what really is important is intelligent input generation, not on try to cut the corners and execute, because the reason why we need to do better input generation is because the longer execution becomes, you need to be very careful in generating what is the next input to try. Because you cannot make up for that loss easily from doing 15-minute invocation of a hardware simulator if you are just trying to do some neighborhood search or search-based testing or generating next input in the neighborhood, right? That kills it because execution latency is so high, right? And the work that I did in terms of execution feedback was because I needed a better feedback to do better input generation. So the goal was really trying to do better input generation by doing some of these optimization. Which is now, I'm going to now like say, then I wrote a lot of things in the bottom, like, you know, like errors, like documentation, like what are the customization we can do. And that's the next part of my talk. I'm about 30-minute mark, and I think I have a 45 minutes. Is it right? Okay. So now I'm going to talk about the vision for low-cost custom fuzzers, and I'm going to talk about 4 ideas. One of the ideas we have started with the custom mutation synthesis, and that's what I'm going to talk about. And the later idea is a little bit more like ongoing or ideas that our community together is cooking. So now let's think about why custom mutation synthesis. So I realized, and a lot of other people have been realizing, that this hardware accelerator, what's really driving this machine learning and deep learning, is actually compiler ecosystem that maps it to different hardwares like a GPU, FPGA, or ASIC, or different, you know, like RTL. And that's what people call as a like deep learning compiler, but it's not a monolithic compiler. It's actually a compiler ecosystem where everybody is building different layers of a compiler. And what drives some of these innovation is what they call as a multi-layer IR. You know, it's actually extensible compiler framework. And what's interesting about MLIR is that it's not a language like it's more of a format. It's like, is it JSON language? No, it's more like a format, embedded format that other things that could be embedded. So in this multi-layer extension, MLIR, people are building what they call as a dialect. Anybody could define their own IR in terms of operation and, you know, operand semantics. And then people then build this, what they call as a compilation path. And if you look at some of this LLVM, Onyx MLIR, which is deep learning, Triton is for like, again, like deep learning kind of a, like middle layer compiler. Circuit is a like consortium of a hardware design, you know, like a deep learning and hardware accelerator compiler. If you look at like number of dialects, it's not a single dialect. It's actually evolving number of a dialect. So now you're thinking, can I build a C-Smith if ecosystem and IR is changing almost every day? You can't, because the C-Smith is possible to build and maintain because IR stays mostly stable, right? Or language stays stable. But now we're facing this fast evolving language ecosystem where it's extremely difficult to fuzz. So this is like challenge 1, dialect specific grammar is needed. So, you know, MLIR, if there's a based format, just like a JSON, but if you do it, then operation makes no sense. What you need is something like a hardware dialect where operation means like hardware module or like hardware, you know, output. The second challenge is, again, which a lot of people in this community recognize, semantic constraints must be, you know, preserved during this generation. You know, in hardware dialect, for example, you know, values, there is a similar to like a C or other language fuzzing domain, you know, these are like values cannot be redefined in the same scope, or attribute values must match the previous definition. So there's a def use constraint. So the question is, how can we bootstrap this dialect specific generator without significant manual effort? The idea that we had is we could potentially consider synthesizing custom mutator operator that's likely to work well in a given domain. And that actually goes back to some of the earlier work I did on code clones or automating similar edits by learning from example patches. Well, we realized that, we may not have a lot of what is a domain-specific constraints, but we do have existing test cases. So if we could make mutation that's likely to work in that given domain by learning from example or coming up with a parameterized mutation, then the likelihood of generating reasonable input that embeds these semantic constraints in a given domain is likely to work really well. So if you look at it, really, what I would like to say is that, again, if you do this customization, you do improve coverage, which is, one of the metric that we do care. But what I want to emphasize is that if you compare that boost that we get compared to MLIR Smith, which is the custom generator that's written with a lot of manual effort, it really happens more when the domain uses more dialect. Why? Because MLIR Smith or these techniques are actually released not too long ago, but they cannot keep up with the language evolution or language addition that's happening in this domain. So it becomes quickly outdated, and therefore that gap is still there when new dialects are being added. The another thing that we looked at is measuring the IR generated IR's quality in terms of input space coverage. So when you do compiler fuzzing, you could generate very long IR, but what really matters is a control and data flow dependencies that are interesting and well connected so that it's producing reasonably interesting semantic program. And again, when we compare our technique since fuzz against MLIR Smith, which is a custom generator, we do come up with a better way of generating these reasonable input in terms of control flow and data flow dependencies, because we're likely to preserve more of a semantics doing these custom mutation. Let's now go into 3 ideas, which is I will not claim an idea of my own, but with the hope that we all talk about them, what are the problems that are there. So I think, many people, including Andreas and Caroline and some of the people worked on this domain. And, I also came to the same realization that language-based, grammar-based fuzzing is really effective way to go, but refined grammar is really needed. What you see on the left is a JSON grammar, which will produce a random thing. But if you want it to work for AWS Cloud Formation, you need each keys and values to mean meaningful names or have a meaningful dependencies. I already talked about MLIR-based grammar and hardware dialect grammar. So sampling from pre-existing generalized grammar alone is definitely not useful, because even if you have a grammar, if a grammar is too coarse to represent domain-specific knowledge, it's not very useful. So when I was playing, I'm going to now share, and then maybe what I am thinking as a problem in this domain, not necessarily solution, and I hope we as a community think about it. So and we know, there are many grammar inference techniques out there. And I played with it too. And, we do the experimentation. And then here's what I learned. A lot of these techniques actually learn using what they call the off-the-shelf input validator. And then it does see the input, and then it start generalizing it. And then it calls that input validator. Once it identifies mergeable structures, which they call bubbles, right? Like a bubbling up, then they recognize these things on the fly. And then I find that it actually doesn't work very well, because it often generates a grammar that overfit. So either you cannot generalize, meaning you generalize very specific grammar that incompensates, only the example that you have seen. The other problem that I see is that the assumptions of a validation is unrealistic, because mostly they are using parser as a validator, when validator in real world should have not only encode the context-free grammar constraint, meaning parser, but they should also encode semantic constraint. So what I'm really thinking is that I recognize this is really a problem. And what I am asking us to think about is what kinds of additional information and how, where we can actually make some breakthrough in this domain, right? And then, our group also has some ongoing work in this domain, but I really think we need to come up with the one is like coming up with a grammar that could serve as an input constraint. The third idea is a lightweight DSL for semantic constraint. And, many of you attended some of the work and presentation yesterday from like Fandango and other related maybe work that are concurrently going on at the time. We all know that grammar is not enough, right? Like input grammar generated by grammar-based fuzzing does not satisfy semantic constraints that are context-specific. And these are context-specific constraints, such as like what kinds of references you should make sense, or it should be like not redefine what's been there. It could be length constraint. There are a lot of semantic constraints out there. So I'm really excited because I think there are right now a lot of interesting work going on in terms of coming up with a lightweight DSL for expressing these semantic constraints. Good examples are like MLIR or Fandango, which represent that both in terms of logical constraints or some of the search goals on the fly. There has been work on semantic annotations, like a polyglot, where you could represent these annotations. My group also has been working on some of this work on programmable annotations that could serve as a pre and post conditions or goals that works with these kinds of generation, as well as a capability to express this constraint using more existing programming construct. So I think, this is a really exciting time because the semantic constraints could serve as goals for regeneration and repair, right? Which will increase the likelihood of generating reasonable input. And if you look at some of these like work that's being published or has been published, these are showing tremendous potential, and I'm really excited. Not only that these kinds of input constraints serve in generating, better well-formed input, they also do pretty well in terms of K-path coverage of, valid or generated input. In our group, we've been also looking at like input diversity because, as I said, like learning constraint, what is the goal of a learning constraint? It not only satisfy well-formedness, but you should provide the diversity of a generated input. And, this type of programmable annotation seems to do really well in increasing input diversity. And so I think I have a lot of hope currently in ongoing work with like many teams in this room where, it's being able to express the semantic constraint will give us a significant bootstrap in terms of generating what we want. Then my last point is now I talked about grammar as a constraint and lightweight DSL. I think maybe we should strive to make this to be automatically generatable or at least semi-automatically bootstrappable. So I think along this line, again, I'm recognizing very exciting work that's actually using like documentation and specifications to learn these constraints for like open API fuzzing or REST API fuzzing. Some of the work is refining and learning constraints for deep learning compilers, which has a very complex shape and type constraint. And also, I think some existing work that I see more potential is LLM-guided fuzzing that actually looks at even implementation of a code to be tested. So I think some of these ideas, it could really hopefully bootstrap this semantic constraint. So this is what I'm thinking again, that picture that I hope you could take away. I think there are perhaps like 3 different dimensions of a customization that we could foresee, right? And I'm envisioning a future where these customization components could be inferred and learnable and pluggable. So today, I talked about this like reflection of my experience of big data analytics and heterogeneity, where I was really facing these challenges of making it work in this long latency, like data intensive and compute intensive long latency domain. I reflected on like kind of effort that went into building custom fuzzers, right? Again, like maybe it could be, it generate a paper, but then at the cost of doing a lot of, customization work. Now we are thinking about how to bootstrap and scale for different domains really easily, partially motivated by ecosystems such as an MLIR compiler. So I think in summary, you have seen there's a like customization effort to make it work for many different domains. I think automation can take in many forms, like search goals for generation, feedback guidance, input constraints, and repair rules to make inputs satisfy semantic constraint. And this is a picture that I hope, again, you could remember. We started from like AFL or these type of vanilla fuzzers, which gave us a tremendous excitement about effectiveness and efficiency. And some of the ones that are being really respected in industries are these like fuzzers that are what we call smart and intelligent, that actually knows more about domain specificity, but it came at a cost of like somebody really understanding domain and then encoding it. And perhaps what we could envision is this future where these components could be potentially customizable and pluggable and learnable, right? That it will work with this existing framework of fuzzers and mutational fuzzers, but will be inspired by these information from error messages, documentations, and also specifications so that we could design this pluggable component. So with that, I would like to thank my former students and postdocs who worked on this domain. And without them, I would not be able to do this work. So thank you. And with that, questions.